Welcome to the last week of this course. So today we are going to learn about confidence interval estimation, and in this specifically we are going to look at difference of two population means, ratio of two population variances, and differences of two population proportions. So last week we have seen confidence interval for single sample problems. So there we had a single mean, single variance, or we had a single proportion, in the sense that you have a population and you just draw a sample from that, and based upon that we are trying to find out the confidence interval estimates. However, in certain situations, or you can say that in your real life, you may come across two populations and then we have to draw samples from both of them, and we need to find out the confidence interval estimates for the difference of the two means, or you could talk about the ratio of the two population variances in both the samples, and then we can talk also about the proportions. So this is about the confidence interval. In addition to this, we are going to learn about bootstrap confidence interval. So let us start with the first one, that is confidence intervals for difference of two population means. In this category, we are going to talk about the three setups. The first one is when the populations are independent and normally distributed with unknown common variance sigma square. So you have two normal populations, and from there you are going to draw samples, and these normal populations are such that they are independent of each other and their variances are also same. In that case, the interval that you calculate is referred to as two sample pooled T interval. The next condition can be when these variances can be different for the two populations. In such a scenario, we refer to it as Welch T interval. And the last one is when the populations are dependent and normally distributed, which basically gives you the pair T interval. So these three cases will be studied under the confidence interval for the difference of two population means, that is mu1 minus mu2. So now if you see over here, we are basically going to utilize the concepts that you have studied in your week 5. So week 5 was also for the sampling distribution when you have two sample problems. In that case, where we studied different cases basically, and we will see how these confidence interval estimates are utilizing the information that we obtained in that week. So let us start with the first one. The theorem says that if you have a random sample coming from normal with mean mu1 and variance is sigma square, and here also it is mu2 and variance is sigma square. So in both the cases variances are same and they are independent samples, and you can see the sample size is also, here it is n and here it is a different sample size, we are denoting it by m. Now if you want to calculate the confidence interval estimate for the difference in the population mean, that is mu1 minus mu2, then it comes out as this. So you have the difference of the two sample means plus minus you have certain quantity over here. And where SP, if you remember, we refer to it as the pooled sample variance. And we are familiar with this term as we have studied it in your 5th week. This is an unbiased estimator for the common variance sigma square. So you can refer to theorem 4 in week 5. We are going to utilize that concept over here now. So let us look at the proof. We know that if I define this T as x bar minus mu bar, x bar minus y bar minus mu1 minus mu2 divided by this term standard error, it follows T distribution with parameter over here with the degrees of freedom n plus m minus 2. So what you see in this case is we have obtained this already, right? The sampling distribution is already there with us. Now we need to use it in this case. So for this, we have the simple criteria. If you remember in the last week also, we have been doing setups like this. So here you can look at the t distribution somewhat like this. So here you will have your minus t alpha by 2, right? And this side you can have your t alpha by 2. So this area is basically alpha by 2. And this side also you have alpha by 2. So in between you have 1 minus alpha. So with the corresponding degrees of freedom. So we are basically looking at the area between these two. So what it will be? So if t is this is your t, so basically we will write that t over here lies between minus t alpha by 2 over here, and it goes up till this, and this probability is 1 minus alpha. Now we can basically simplify this. So here we can take this term over here can go to either side, and then we get this inequality. Likewise, you can further solve it, and what you will get is that the difference of the two population means lies between these two endpoints. So if you have to calculate the 1 minus alpha % confidence interval for the difference of population means, then it is nothing but the difference of the two sample means plus minus this margin of error. Because if you remember, we build your confidence interval estimates around the point estimates. So for the point estimates, you can think of population mean is there. So for that we have the sample mean, and if there are two difference of two population means, so you could ideally have the difference of the two sample mean as point estimate if you want. And if I want the interval estimate, it means a term, that is the margin of error, has to be added or subtracted from that, so that we get a range of values within which the difference of the population mean, or you can say that mu1 minus mu2 is going to lie. So you can see that the proof is very simple, provided you have this information that what is the sampling distribution of the case when you are drawing from two normal populations which are independent and they have the same variance, because whenever the variance is same, then only your pooled variance would come into picture. To understand this, let us consider this example over here. Suppose the number of products sold by the two sales team A and B weekly are given as follows. Now the question is, based on this data set, can you say that is there statistically significant evidence to conclude that there is a difference in the average number of products sold between the two sales team? So you have to find out what is the difference in the average number of products. So by just looking at the statement, you could identify that we are talking about average number of products. So where you have average, so your mean would come into use, and you will have mu1 minus mu2. So you have to find out the interval estimate for this first, and then we will see what should be the conclusion. What are the observations? You need x bar minus y bar plus minus t alpha by 2, and then you have m plus n minus 2, and you have some term over here, sp into 1 over m plus 1 over n. Yes. So let us see. So these can be your xi's, so I can denote these observations which are coming from team A as xi's, and these could be my yi's. If these are xi's, so I can calculate x bar also from here, and I can also calculate the sample variance. Likewise, I can calculate y bar and the sample variance for this. M and n are equal in both these cases. Okay. Also, what do you need? So you can consider 95%. So you can look at t value at alpha by 2. So let us see what is the solution. So we have assumed that xi and yi are the number of products. So team A is xi and team B is yi. Sample variances, basically in this case, they are very much close to each other, 6.05 and 6.63. They are not very different, so you can assume that the population variances are similar. Once you have made this observation, you can use your pool t interval. Had they been different, you would not have been able to use this result over here. because then in that case you would be using the other result which we are going to see next. Now if you calculate the pooled sample variance, it is basically m minus 1 sx square over here, and then same m minus 1 into sy square, m plus n minus 2. So this comes out as 6.68. Okay, so the pooled variance is there. Now we can calculate this pooled standard deviation because we are ideally going to use this value in the formula. Now when you look at the t value from the table, or if you are using any software from there, if you look at these 2 degrees of freedom m and n at 21, then 95% confidence interval. So T alpha by 2 would be 0.025, because if you are considering 95%, so 1 minus alpha is basically your 0.95. So alpha is basically your 0.05. So alpha by 2 would be 0.025. Right? So if you look at this degree of freedom and alpha value, you would get 2.021. So you can easily read these tables, and it is given in any standard textbook. Behind at the end they give certain tables, you can go through them. Now since x bar and y bar from the data we can calculate, and we can finally substitute it over here. So this is your mean over here, x bar minus y bar. This is basically your t value, this is sp, and this is 1 over m plus 1 over n. And if you simplify this, solve this, the interval that you get is this one. So you see that the difference of the two population means that mu1 minus mu2 lies between these 2 points, right? Note that this interval does not contain the value 0. So we can conclude that the two population means differ. Why we are saying that? Because see, mu1 minus mu2 takes value between 1.25 to 4.47 approximately. Had it included 0 in this interval, it meant that mu1 minus mu2 would have taken 0 at some point of time. It would have taken this value. It means that mu1 would have been equal to mu2. It means the two teams, sales team, are the average is same for them, right? However, here in this case what is happening is that they are not same. It is not in considering 0, it is out beyond the 0 point. So in that way you can say that there is a difference in the two population means, because here it is not happening. Now let us move on to the next result, which is Welch t interval. In this case what you see is that the two variances are different. So the result is that if the data is normally distributed and the population variances can't be assumed to be equal, right? They are not equal like in the previous case, then same thing here, you would assume x bar minus y bar, okay? And here it would be T alpha by 2 is same, the degrees of freedom over here is changing, and in that case since we have the pooled variance, so that, and it is common to both of them, so it basically goes outside this square bracket, right? So here it is xx square and sy square. So you can use any notation. If you are using mu1 mu2, so you can keep s1 square s2 square. If you want mu x mu y, so you can keep sx square over sy square. So whatever you do, you can, it is fine. Within a result or within a theorem, at least be consistent within that. Now where the degrees of freedom are would be approximately this. If you recall, we have used this result earlier in your week 5. Basically it was theorem 3 in the 5th week. So there you remember we used this, instead of r we wrote it as beta, or beta hat was there, right? So it was a t distribution with this parameter over there, beta hat, right? So instead of beta hat we are writing r over here just to denote that it's the degrees of freedom. So we already obtained that sampling distribution in that case, where the two variances are different. Now we just have to easily use it. in our result. So let us see the proof for this. It is very simple, just on the same lines as we have done earlier also. So let me show you that. So here what we have is that t, which is x bar minus y bar minus mu x minus mu y over sx square over n1, okay, whatever it is, I think n or m, so sy square over, so let me use n and m. So n and m, okay, this followed t distribution with this parameter, right? So this was one of the result in your fifth week, sampling distribution week. Now we can easily use the same concept. So here basically it shows that if I consider this area in between, so here this would be minus t alpha by 2, right, and r degrees of freedom, and this side it would be t alpha by 2 at r, or I could just, instead of beta hat, I could replace this with r only, because if you can cross check, it is r and beta hat the same quantities. So it is this alpha by 2 this side, and this is alpha by 2, and here you have 1 minus alpha. If you have to solve this, so basically we can simply write it minus t alpha by 2 r at r degrees of freedom. So this t would come in between, so x bar minus y bar minus mu x minus mu y whole divided by sx square over n plus sy square over m. This is less than equal to t alpha by 2 r, and this would be 1 minus alpha. So if you simplify this further, what will you get? You will get that x bar minus y bar minus t alpha by 2 at r, this one would be sx square over n plus sy square over m. This one would be less than equal to mu 1, so mu x minus mu y, this is the we want the interval for this, and here again it would be x bar minus y bar plus the same quantity, right? So if you can recall, we have written the same thing in the slides also, and the proof is very easy actually, nothing difficult in this case, right? It only depends that you know this sampling distribution, and that's the reason we studied those concepts earlier. So now it is just very simple to apply them. So let us look at the example. So if you consider the same example, we were given the following statistics. So n sample sizes were given, and sample means and sample variances for both of the two samples were given to us. Now the question is, what is the difference, if any, in the mean number of products sold by the two sales team? So in this case, we need to calculate R first. So R would be approximately 40. So we are just substituting the value, right? This is the formula that you know. We will substitute, we know each of these values, right? Sx square, sy square, n and m we know. You just substitute these values and you would get the value of R. Now if you use the t table, then from there you will have, at this degrees of freedom, right, t alpha by 2 R. So this basically comes out as 2.021, and the Welch interval in this case would be simply, so this is basically x bar, y bar, this is your t value, t alpha by 2 at r degrees of freedom, and in this side what do you have? Sx square over n plus sy square over m, right? So the formula that we have obtained, so we are simply substituting it. So the interval that you obtain in this case is 1.360 to 4.360. Now if you recall from the first example, so we had the same setup and we have solved it using both the theorems. So in the first result, or the first theorem, we obtained the two sample pool t interval. If you apply that concept, then the interval was this, 1.250 to 4.470, and in this case it is this. Even if you're considering them different, the reason is that they are not that different here. Why? Because the sample variances are really not different. Because if you see over here, sample variances which was given to us, in this case, you see, right? So either you can consider them same also, and you can consider them different also. Okay, you can use both the methods, and in both the cases you would get the same thing. But the rule of thumb is that now you can use it, as I told you earlier also, that Welch T interval could be used if this category is satisfied, right? So in this case you can assume them that they are same, and you can just simply use the pooled T interval, because actually finding the T, or you can say this Welch T interval, is a little bit lengthier process. Now we come to your third situation, which is paired T interval. Now what we have seen till now, we have made the assumption that the two populations were independent, right? And it was coming from normal, they were independent, and in one case the variance was unknown, but they were same, and in the other case they were different. Now in this case we consider that the practical situation that okay, they can be dependent, right? In real life we often come across situations where these two set of observations would be dependent, and we have talked about this earlier also. So when we are dealing with dependent measurements, you can calculate the sample mean, and the population mean difference could be evaluated as this. So D bar is basically, if you can recall, last time also we had that. So basically you will have xi's, if you recall, xi's and yi's would be there, and then we basically calculate their corresponding differences, right? These are the observations. We calculate the corresponding differences, xi minus yi. Now based upon this, you can calculate your D bar also, you can calculate the standard error also. T alpha by 2 is already given to you, and it is very easy to see how it is coming. So let us see the proof for this. So here only let us see the proof for this. So we know that if you have D bar minus mu D divided by SD over root n, this follows T distribution with n minus 1 degrees of freedom. So now again same thing we can use, minus T alpha by 2 less than equal to D bar minus mu D So here it would have the degrees of freedom n minus 1, and this side also. This probability is 1 minus alpha. If we just look at this interval now and simplify this, so what it will be? Minus T alpha by 2 at n minus 1 degrees of freedom, you have SD over root n is less than equal to D bar minus mu D is less than equal to T alpha by 2 n minus 1 SD by root n. So finally, if you solve for mu D, because that is your parameter of interest, so this would basically be D bar minus T alpha by 2 at n minus 1 SD by root n, and this side it would be D bar plus T alpha by 2 n minus 1 SD by root n. And this is the interval that we wanted, D bar plus minus this. So again, with just the idea of this sampling distribution, we have solved it, and we have seen this. If you can go back to your week 5 and see the corresponding result when we obtained the sampling distribution for your paired t-test, when you had dependent measurements. So this is basically theorem 6 in week 5. So now let us look at the example. Suppose you want to investigate if the installation of a new air filtration system in a factory has had an impact on the level of specific air pollutant in the factory environment. Now the collected data on the concentration of this particulate matter before and after the installation of the filtration system for 10 different days is given to you. By just looking at the problem, you can identify that we are considering paired values over here, because we are looking at what was before the installation, what were the values, and after the installation. So there is some sort of dependency between those two pair of measurements. So the data that is given to you for 10 days is this. So this is basically your xi's and this is your yi, right? I can easily calculate di now. So if you look at this solution over here, so xi and yi's we are denoting. So you can calculate this value. So based upon this, you will have d bar and sd also. Right, this is the form because just T alpha by 2 at n minus 1 degrees of freedom. So n here is 10, so n minus 1 would be 9. So 7.4, that is d bar, plus minus, this is the t value, and this is your SD by root n. So this comes out as 6.241 to 8.599. So again, you can see from here that this does not include 0. We can conclude that the installation of the filtration system has a significant effect in reducing the particulate matter. Why? Again, because had it been, if mu d had been 0, it means that there is no difference. Before and after, there is no difference. So since it is not 0, it means that the new installation that has been done has an impact or has a significant effect in reducing the particulate matter. So with this, we complete the confidence interval for the difference of the two population means. Now you can look at the confidence interval for ratio of two population variances. So we know that immediately when you have a single population variance, then you will have sample variance, and in that case the distribution involved would be chi-square. And if you have two such variances, sigma x square over sigma y square, again you will have sx square over sy square, and the distribution in this case, because both would be chi-square divided by their respective degrees of freedom, that would eventually be following your F distribution. So this much you should be able to immediately get when you read any particular statement, right? So by just looking at this heading, you must have come to know that, because you have been attending lectures from the first week, so you know by now that it is going to follow the F distribution. And we are going to make use of the sampling distribution thing that we have already studied. So let us see what is the result. The result says that if you have a random sample coming from normal distribution with mean and variance given to you as this, and you have another sample which is coming from the different population with different means and variance, then your sample, which is, you can see the sizes are different, they are independent, then this ratio is basically, the confidence interval would be this, right? So you can see sx square over sy square, this is same in both of this, only this quantity is changing, right? Here you have 1 over f alpha by 2, and the degrees of freedom is reversed in this situation. So let us see what is the proof for this. To prove this, we are going to utilize this concept we obtained in your initial lecture, that was week 4, right? The sampling distribution. For the two samples, because they are coming, so these two would hold true. Now if I add them also, then also you would have your, so that is not basically criteria over here. So we need basically the concept of independence between the two samples. So you have this first chi-square and the second is also chi-square, and you have divided by their respective degrees of freedom. So if you have a random variable u following chi-square with r degrees of freedom, and v is there which is following chi-square with suppose s degrees of freedom, then if you divide u by r and v by s, right, then it would follow F distribution with r and s degrees of freedom. This we know. So we are just simply substituting the two chi-square, we have divided it by their respective degrees of freedom. Terms would cancel out, right? m minus 1 and n minus 1 would cancel out. What we will be left with this, and we know that if we are doing this transformation over here, like not exactly transformation, we are dividing it just by the respective degrees of freedom. So it would follow F distribution with m minus 1 degrees of freedom and n minus 1. Right, now we know how your F distribution looks like, because in this case it is not like a symmetric one, but it is somewhat skewed. So here you will have one value, and this side it would again be alpha. So you have f1 minus alpha by 2, and this is f alpha by 2. So this is the area, that is alpha by 2, and this is 1 minus alpha, and this is alpha by 2 again to this side. So it is basically the f value such that the area to the right of it is alpha by 2, and in this case it is the f value such that the area to the right of it would be 1 minus alpha by 2, because alpha by 2 is to its left, so the remaining one would be 1 minus alpha by 2. Now we know that this quantity is following F distribution, so it would fall between 1 minus alpha by 2, these two things we know. It would fall as we have done earlier also. Now you can simplify this. Before simplifying, it is easy to see because we just have to look at this, right? Sigma x square over sigma y square. We need an important result over here. We use this. So you know that since if you have x following F distribution with m minus 1 and n minus 1 degrees of freedom, so 1 over x would follow F distribution, and the degrees of freedom gets reversed. So basically this result over here follows from this common concept. So you replace, because here you have f 1 minus alpha by 2, so instead of that you can write 1 over f alpha by 2 n minus 1 m minus 1 degrees of freedom. Okay, so the corresponding 101 minus alpha confidence interval would be this. So you take Sx square. Okay, so here this Sx square would go in the numerator, Sy square would come in the denominator, and this is basically your result. So in this we are considering again the same example, and we want to see the ratio of the two population variances. So for the ratio of the two population variances, we need Sx square over Sy square, right? That is given to us. And what else do we need? We need F values. F would be alpha by 2 at the corresponding degrees of freedom, because here both are same. We need this and 1 over that. You can see that F alpha by 2 at m minus 1 n minus 1, so it will be 2.47, and if I look at 1 minus alpha by 2, so it would just be 1 over this, right? So even if you don't know this value, you know the relation that it would be same as F alpha by 2, it would be this 1 over 2.47, so it is easy to calculate. And finally you can just substitute it, because this one would come here, Sx square over Sy square, and same things here, right? So you get the 95% confidence interval in this way. Finally, we move on to the confidence interval for difference of two population proportions. So the result over here says that for large random samples, an approximate 101 minus alpha % confidence interval for the difference in the two population proportions, that is P1 minus P2, would be this. Again, similar concepts we have seen, similar terms we have used. So this is your point estimate, and basically this is your margin of error, right? Z alpha by 2, and we have seen these things. So if you look at the proof, it is very easy, because we know that P1 hat, that is the first sample proportion for the first sample, it would be Y1 by N1. So Y1 basically are those individuals who have that characteristic out of the total sample size, right? So it would approximately follow normal distribution with mean P1, and this would be the variance. So we have studied this earlier also. Same thing would hold true for P2 hat also. And now if you have two normal distributed random variables, so their linear combination again would be normal. So here it would follow with parameters mu1 minus mu2, and it would be sigma 1 square plus sigma 2 square over here. And since it is normal, so you would make use of the standard normal table, right? It would be between here in this way, so it would be somewhere here minus z alpha by 2, and it would be z alpha by 2. So this is some shaded portion, and this is, and in between you have 1 minus alpha. So this is approximately, we are using this approximation over here. If you simplify this, what you get is this result, right? Because this quantity in the denominator would get multiplied on both the ends, and you have to solve for P1 minus P2, so ultimately you will get this result. If you look at an example for this, so a marketing research company conducted a survey to compare the effectiveness of two advertising campaigns, X and Y, in attracting the new customers to a retail store. They found that 400 people who were exposed to the first campaign, out of 400, 200 visited. So you can basically calculate P1 hat now, though that will be 200 by 400. Now for the second campaign, what they did, in a sample of 250 people, 100 of them visited. So P2 hat would be again 100 by 250. So you have to calculate now the 95% confidence interval. So basically, if you see in this confidence interval for population proportion, wherever you come across that, you don't need much quantities to work upon, right? You just need the sample proportions, you know the sample sizes, obviously, and you just need the z value, right? Alpha by 2, basically at what confidence level you have to see. And if you are having those values, your job is done. So in this data set, again, you can see that this is given to you. So sample sizes are given, number of people who visited is given, and you can calculate the corresponding proportion. So this one is your P1 hat and this is your P2 hat. So this basically, it would be P1 hat minus P2 hat plus minus this 1.96, because we have been using it, z alpha by 2. If it is at 95% confidence interval, so basically this quantity would be 1.96 at 0.025. So again, you have P1 hat here. This one is again 1 minus P1 hat. So again, it would be 0.50. You are dividing it by n. N1 we can say. Again, this is P2 hat into 1 minus P2 hat. And this is your N2. You solve it and finally what you get is this answer. So you can finally conclude that we can be 95% confident that there are between 2.2% to 17.8% more visitors to store due to campaign X than campaign Y. So it is finding this, right? It is the interval for P1 minus P2. So it shows that it is coming somewhere around between 2.2% to 17.8%. So it means that your first campaign, that is X, campaign X, is more effective in gathering the customers. Okay. So with this, we complete the concept of confidence interval for two sample problems. And please keep in mind that confidence, whenever we are talking about confidence intervals, we always say that we are 95% or 99% confident that the population parameter is going to lie within these 2 points. Do not make a probabilistic statement about that. So in this week, we have one more concept that is left that we will cover in the next lecture. That is about the bootstrap confidence interval. So we will look into that. Thank you.